Hello, everyone. So, to finally round out our lesson on modular arithmetic, we're going to sum up all of our knowledge and go through a couple problems testing the very barriers of what we know so far. So, here's just an example. Here's what we have proven so far, where if A1 is congruent to A2 and B1 is congruent to B2 under mod M, the sum of A1 plus B1 and A2 and B2, the sum of each is congruent under mod M. The product of A1 and B1 and the product of A2 B2 are congruent mod M. And A1 to the nth power is congruent to A2 to the nth power mod M as well. So, let's tackle the first problem dealing with all the tools that we have in our pocket, I guess, or whatever. Alright, so find the remainder when 5 squared is divided by 7. 5 to the third is divided by 7. 5 to the fourth, so on and so on and so on. So, let's see. There seems to be a pattern. It wants to see the pattern when the exponentiation keeps increasing. So, in fact, to start this problem, I'm going to start at 5 to the 0th power, 5 to the first, and then go and work my way up to 5 to the 8th. So 5 squared, 5 to the third, 5 to the fourth, 5 to the fifth, 5 to the sixth, and 5 to the seventh, and 5 to the eighth. Well, let's start out. 5 to the 0 is just, anything to the 0th power is 1. So it'd be 1 mod 7. Five to the first power is 5, and 5 is just 5 mod 7. 5 squared. 5 squared is 25. And under division with 7, well, 7 times 3 is 21, plus 4 would get me 25. So my remainder would be 4. So 5 squared is congruent to 4 mod 7. Next, 5 to the third power. Well, that's just 125, and alright, 125 divided with 7. It goes in 1, 7 minus is a 5. Drop the 5. 7 goes into 55 7 times, so that's 49. And 55 minus 49 is 6. So it'd be congruent to 6 mod 7. Now the numbers are getting big. Is there any way we could just do this easier? Well, we could use the properties of our product. Like, for instance, instead of doing all of this mumbo jumbo, 5 to the third is just the same as 5 squared times 5 to the first. Utilizing our multiplication properties, this is going to be, I know 5 squared is 4, and I know 5 to the first is 5. So this is going to be equal to 20 mod 7, which, depending on how you look at it, like, 7 times 2, 14, plus 6 would give us 20, so we'd have a remainder of 6. You could do 7 times 3 is 21, minus 1, so if my remainder is minus 1, it would get me to 20, and minus 1 on mod 7 would bring me to 6 as well. So it just depends on how you want to work it out. So 5 to the 4th. 5 to the 4th. Well, that's 5 squared times 5 squared. Which is, 5 squared is 4 and 4. Which is congruent to 16 mod 7. 4 times 2 is 14, plus 2 is 16, so our answer, the remainder, would be 2. Mod 7. Hopefully we're beginning to see how these exponentiation tricks will help make these problems in our life a little bit easier. So, 5 to the 5th power, well, that would be, 5 to the 4th times 5 to the 1st, which would be the same as 5 to the 4th is 2. 5 to the 1st is 5, which is 10, and under 10 mod 7. 10 mod 7, giving us 3. And you should be able to try the rest out on your own, so I'm going to go through these, assuming we get the gist of it. 5 to the 6th power. Well, that's the same thing as 3 times 5, 15, which would have a remainder of 1 when divided with 7. 5 to the 7th power. Well, that would be 5 to the 6th times 5 to the 1st, which is just 5 times 1, which is 5. Mod 7. 5 to the 8th. Well, that would be 5 to the 4th times 5 to the 4th, which is 2 times 2, which is 4. Mod 7. So, what do we see happening here? Well, our pattern is repeating. 1, 5, 4, 6, 2, 3. 1, 5, 4. And you can bet if we were to extend it, 5 to the 9th. Well, that would be, the same thing as 5 to the 8th times 5 to the 1st. 5 times 4 is 20, which we know is the same thing as 5 to the 3rd, so it's going to be 6 mod 7. And the pattern is just going to repeat. 1, 5, 4, 6, 2, 3. 1, 5, 4, 6, 2, 3. So on and so on and so on. All the way down. And all the answers are, they're repeating. And we can also just break down these exponents into combinations that will make the results pretty easy to find. So let's think about what's going on. It includes all the 6 modulo 7 residues. So it includes, all the 6, the 0 isn't appearing. So it's just 1, 2, 3, 4, 5, 6. Those are the only values we're getting. So when we're asked to find, I think it was 5 to the 2005th power. Okay, well, it's along this chain of answers that are just 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So, how can this help us out? Where does this get us? Well, if we look at the exponent itself, we see that 2005 is congruent to 1 under mod 6. Now, why would I do mod 6? Aren't we working in mod 7? Well, the repeating answers we're getting along this exponentiation chain are 6 values, right? And if we want to find whatever pattern it lies within that 6 values, it's the same thing as division by 6 or mod 6. So we just do this to note that, all right, 2005. And we could do this like, think of it like when we first started, our very first problems. Where we didn't even know about the modular system. The very first problem in this entire lesson sequence. Where we just want to, if we knew a sequence had 6 particular terms or 6 values, then we would divide by 6 to find our answer. Noting that, all right, 6 times 3 is 18. Due to long division, 2 drops down to get a 20 again, so we get a 3. 18 minus gets us another 2. Drop down the other 0. Again, 3 and 20. Drop, 18. Drop down to get 2 and 5, which would mean 6 goes into 25 4 times with our remainder of 1, because 25 minus 24 is 1. And then we would know that, all right, using that old logic, we would say, all right, so the pattern is going to repeat 3,334 times along this series of this sequence of values, right? So the sequence of values goes 1, 5, 4, 6, 2, 3. 1, 5, 4, 6, 2, 3. This is literally just the very first problem we ever did in this lesson sequence. Just a different version of it. A little bit more involved. So the pattern of 1, 5, 4, 6, 2, 3, this pattern of 6 values repeats 3,334 times, and then begins the first time, or it begins with the first letter in the next sequence but stops there. We have 1 leftover term. Now, because that is true, and because these exponents are just generating these same values, what we have is that 5 to the 2005th power. Actually, let me write it. I get all jumbled up. Let me write it up here, where all the rest of the work is in the pattern. So 5 to the 2005th power is congruent to, well, we know that it's got to be congruent to 5 to the first power. Because of these combination of values that we're getting. And that would just be 5 to the 2005th power is congruent to just 5 mod 7. So this is informing us that our exponents have a sort of pattern in them on their own. For example, we have like 5. The fifth exponent corresponds to the third term in the sequence. The sixth exponent corresponds with the first term in the sequence. And if we think in terms of mod 6, well, 7 mod 6 is 1, so it would correspond to 5 to the first power, which it does. 5 to the 8th. 8 mod 6 is 2, so it would correspond with 5 to the second power. And we just use that logic where the 2005 is going to correspond to the first power, since the remainder is 1. Now, there is one other way we could have done it, which is use those rules that I was using earlier. So 5 to the 2005th power, and we can break up this exponentiation. But you got to be a little bit clever with what's going on. So, for instance, this is 5 to the first times 5 to the 2004th. And 5 to the first times, well, the 2004th power, that's a multiple of, I should do congruent symbols. That's a multiple of 6 to 2004, like we saw earlier. So this is going to end up being 5 to the 6 times 334, like we found earlier. And that's congruent to, well, that's 5 to the first times 1 to the 334th power, which is the same as just 5 times 1, which is just 5 mod 7. So there's a lot of different ways we could have come across this pattern. We could see how they're related to each other. We still have to do that kind of mod 6 division to get answers that we like. And this kind of lets us see how it's like all related. Like we have, this is 0 mod 6, but with our remainder of 1. Thus getting us that 2005 is just the same as 5 to the first, which is just 5. So always be on the lookout for patterns. Math is the process, or the kind of like the science of finding patterns in numbers and structures and stuff like that. And in the modular system, we have plenty of patterns to find.